the expanding universe right now, space itself stretches faster than your imagination can handle. Galaxies are not simply drifting through the void like cosmic travelers, they are being carried away on a fabric that grows larger every second. This isn't motion in the ordinary sense. It's the expansion of the stage upon which everything plays out. Imagine this. The emptiness between galaxies acts like an invisible rubber sheet. That sheet doesn't sit still, it stretches. As it stretches, the distance from Earth to the nearest star increases ever so slightly. The scale of reality itself inflates. We tend to think of nothing as truly empty, but space is not nothing. Space has properties. It can bend around massive objects, ripple when gravitational waves pass through it, and most astonishing of all, expand. This idea smashes our intuition. If you blow up a balloon, it grows because the air inside pushes against the room around it. But the universe has no surrounding room. Space expands without expanding into anything else. It creates more of itself as it grows. Think of it like this. Suppose you live on the surface of a balloon. You can only move across the balloon's skin. You cannot look up or down to see the third dimension. As the balloon inflates, every point on its surface drifts away from every other point. From your two-dimensional perspective, the universe is simply growing. There's no outside, it expands into only more surface. Now take that balloon analogy and add one more dimension. That's our three-dimensional reality. Space grows in the same way, without needing a surrounding container. Scientists call this intrinsic expansion. This expansion happens everywhere at once. Between the atoms in your body, the effect is so weak that the electromagnetic force is binding. You together win. Between the stars of our galaxy, gravity dominates. But between clusters of galaxies separated by millions of light years, expansion overwhelms everything. There, nothing can stop the stretching fabric of the cosmos. And the numbers? They stagger the mind? A region of space 1 million light years wide grows by about 22 meters every second. Galaxies millions of light years away recede at hundreds of thousands of miles per hour. Not because they're racing through space, but because space itself carries them along like passengers on a cosmic conveyor belt. This revelation began in 1929 when astronomer Edwin Hubble pointed the world's largest telescope at the night sky. At that time, most scientists, including Albert Einstein, believed the universe was static and eternal. Hubble expected a calm, steady cosmos. What he found instead was chaos, galaxies fleeing in every direction. The farther away they were, the faster they receded. It looked as if Earth sat at the center of the universe, with galaxies rushing away from us like startled birds. But that was an illusion. From the viewpoint of any galaxy, the same thing would appear true. Each one would see itself as the center. This is not because there is a center, but because expansion happens uniformly everywhere. Hubble uncovered this truth through the fingerprints of light. Every element glows at exact colors when heated. Hydrogen shines at a specific red wavelength, helium at a precise yellow. But when Hubble studied distant galaxies, those familiar colors appeared stretched toward the red end of the spectrum. The farther away the galaxy, the more stretched the light. This redshift revealed galaxies receding at astonishing speeds. The math told an elegant story. A galaxy 2 million light years away moved at about 45 miles per second. One twice as far fled at twice the speed. This simple pattern became known as Hubble's law. The speed at which a galaxy recedes is proportional to its distance. Today, we describe this relationship with a number called the Hubble constant, about 70 kilometers per second per megaparsec. Put simply, for every 3.26 million light years of distance, a galaxy recedes about 43 miles per second faster. The implications shook science to its core. If everything is moving apart now, then long ago everything must have been closer together. Trace it backward far enough, and you reach a time when all matter, energy, space, and even time itself squeezed into a single, unimaginable point. That insight gave birth to the Big Bang Theory, the realization that the universe has an age, a beginning and possibly an end. Even more shocking, Hubble's discovery explained why the night sky is dark. If the universe were infinite, eternal, and unchanging, then every patch of sky would glow with starlight. Instead, much of the cosmos is invisible to us because light from distant galaxies has not had time to arrive. Expansion itself sets a limit on what we can see. And here comes the mind-bending twist. Galaxies farther than about 14 billion light years away are receding faster than the speed of light. How is that possible? Doesn't Einstein's theory forbid anything from moving faster than light? The answer lies in understanding that galaxies aren't breaking the cosmic speed limit. They are not racing through space at superluminal speeds. Instead, the space between us and them is expanding so quickly that it carries them away faster than their light can ever reach us. This creates a cosmic horizon, a boundary beyond which we can never see. Any galaxy past that line is effectively lost to us forever, not because it ceases to exist, but because space expands too fast for its light to bridge the gap. To picture this, return to the balloon analogy. Draw a scatter of dots across its surface to represent galaxies. As you inflate the balloon, every dot moves away from every other dot. Choose one dot, call it the Milky Way. From its perspective, every other galaxy recedes outward, some faster than others. But if you switch perspectives to another dot, say Andromeda, the same illusion holds. From there too, every galaxy rushes away. No matter which point you choose, each appears to sit at the center of expansion. The truth is that there is no center. Expansion happens everywhere, all at once. This realization changes everything about how we see ourselves. Earth is not the center of the cosmos, nor even our galaxy. Every galaxy shares the same illusion of centrality. Reality itself stretches without boundaries or anchors, yet this expansion does not violate Einstein's rules. His speed limit applies to objects moving through space. It does not restrict how fast space itself can grow. Expansion is exempt from that law. Space can stretch faster than light, carrying galaxies beyond our reach. This is why we can never see the entire universe. The observable cosmos is just a finite bubble around us, limited not by technology, but by the nature of reality itself. Beyond that bubble may lie endless galaxies, stars, and perhaps even other universes. But their light will never reach us, no matter how long we wait. So the universe grows relentlessly and without pause. It carries everything along for the ride, from the smallest atom to the largest galaxy cluster. And that growth holds the key to our origins, our future, and the greatest cosmic mysteries yet to come. The Big Bang and cosmic origins. Rewind the cosmic movie. Roll the tape backward. Every galaxy rushing away from us today must once have been closer. Trace that expansion far enough back, and you reach a singular moment of time when everything we know, every star, every planet, every atom, was compressed into something smaller than a proton. The universe itself was born not in space, but with space. This is the Big Bang. The name is misleading, though. Don't imagine a fiery explosion flinging galaxies into the void. There was no void for them to expand into. Instead, the Big Bang was the moment space and time themselves erupted into being. It was the birth of the cosmic stage. 13.8 billion years ago. The entire universe measured smaller than the period at the end of this sentence. Temperatures soared to levels we can barely describe, hundreds of millions of trillions of degrees. Physics itself breaks down when you try to imagine conditions this extreme. In that instant, not only did matter and energy spring into existence, but the very rules of reality also began. And then, in the tiniest fraction of a second after it began, something extraordinary happened. A period scientists call cosmic inflation. During inflation, space didn't just expand, it ballooned at a speed beyond comprehension. In less time than it takes light to cross a proton, the universe grew by a factor of at least 10. That's a 1 followed by 26 zeros. A region smaller than an atom stretched to the size of a basketball. Why does this matter? Inflation explains several cosmic mysteries. Look in any direction, and you see a universe that looks remarkably uniform. The temperatures of distant regions, separated by billions of light years, are nearly identical. Yet, these regions could never have communicated with each other, not even at light speed. Inflation solves this puzzle by stretching a tiny, uniform patch of space into cosmic proportions. It also explains why the universe appears flat. Just as inflating a balloon makes a small patch look flat to an ant crawling across it, cosmic inflation smoothed out any initial curvature. Space now appears almost perfectly flat, balanced on the razor's edge between collapsing under gravity and expanding forever. After inflation ended, the universe was still incredibly hot and dense, filled with a glowing plasma of free electrons and nuclei. For the first 380,000 years, light couldn't travel freely. Electrons scattered photons in every direction, turning space into a cosmic fog. If you had been there, you couldn't have seen more than a few inches in front of you, but then came a turning point recombination. The universe cooled enough for electrons to combine with protons and form the first stable atoms. Suddenly, light could travel unhindered. The fog cleared, and the universe became transparent for the first time. That ancient light still surrounds us today. We call it the cosmic microwave background, CMB, the faint afterglow of creation. Every time you tune a TV to static, a fraction of that noise comes from the CMB. It is literally the baby picture of the universe, a snapshot taken when the cosmos was just 380,000 years old. This light carries crucial clues. Its temperature is astonishingly uniform, matching the predictions of the Big Bang with incredible precision. Yet it contains tiny fluctuations, slight warm and cool spots that mark where matter was just a little denser. Over billions of years, gravity amplified those differences, pulling matter into clumps that became galaxies, stars, and eventually planets. Without those tiny irregularities, the universe would have remained a smooth, lifeless fog. Even more mind-bending, the CMB shows us just how much the universe has expanded since those early days. The radiation we detect today originally glowed as bright, visible light. But as it traveled for nearly 14 billion years, space itself stretched those wavelengths until they became the faint microwaves we measure today. In fact, the universe has expanded by a factor of about 1,100 since the CMB was released. So how do we picture this expansion? Astronomers often use the raisin bread analogy. Imagine dough rising in the oven, studded with raisins. The dough represents space. The raisins represent galaxies. As the dough expands, every raisin moves farther away from every other raisin. No raisin is at the center, and none of them are actually moving through the dough. They're just being carried along as the dough itself expands. From the perspective of any single raisin, it looks like all the others are rushing away, with the more distant ones receding faster. Sound familiar? That's exactly what Hubble observed with galaxies. The analogy reveals two crucial truths. First, galaxies are not flying through space at impossible speeds. They move slowly through their local regions, while the expansion of space accounts for their apparent motion. Second, the expansion affects all distances equally. Just as every part of the bread rises at the same rate, every region of space expands at the same percentage. This is why distant galaxies appear to recede so quickly. Consider 10 billion light-years away. It isn't racing through space at nearly the speed of light. It's just that billions of light-years of space lie between us, and each bit of that space is expanding. Add up all those tiny expansions, and the cumulative effect makes the galaxy seem to race away at breathtaking speeds. And this brings us back to Einstein's great rule. Nothing with mass can travel faster than light through space. But nothing stops space itself from expanding faster than light. This is how galaxies can recede beyond light speed without breaking physics. The consequences are profound. Light from galaxies farther than about 14 billion light-years can never reach us. No matter how long we wait, the expansion of space will always outpace that light. These galaxies lie beyond what we call the Hubble horizon. They exist, but they are forever unobservable. Even stranger, galaxies that we can see today will eventually slip beyond that horizon. Their light reaches us now, but as expansion accelerates, they will cross the boundary into invisibility. The universe we observe will grow emptier with time, until only our local group of galaxies remains visible. But the story of expansion doesn't end there. Light itself carries the evidence of the universe's growth. As photons travel across billions of light-years of expanding space, their wavelengths stretch like taffy. Blue light becomes red light becomes infrared, and infrared becomes microwaves. This process, called cosmological redshift, is one of the most powerful tools in astronomy. It's different from the Doppler effect, where a moving object changes the pitch of sound or the color of light. Cosmological redshift happens not because galaxies move through space, but because space itself expands during the photon's journey. The greater the redshift, the more the universe has grown since that light was emitted. This cosmic stretching not only dims the light, but also encodes a timeline of expansion. By studying redshift, astronomers can map the universe in 3 dimensions, revealing how matter clumped into galaxies and clusters over billions of years. So, what began as a singular moment of unimaginable density gave rise to everything. Vast web of galaxies, the stars that light our night sky, the planets that cradle life. The Big Bang was not a bang at all, but a beginning. Inflation stretched the fabric of reality itself. Recombination let light escape, leaving us with a cosmic memory etched across the sky. And cosmological redshift continues to whisper the story of expansion into our telescopes. The universe is not just old. It carries its history written in light. And as we decipher that record, we uncover not only where we came from, but where we are headed. Redshift and the cosmic horizon. Imagine looking deep into the night sky. Every photon of starlight that reaches your eye carries with it a history lesson, an ancient message from a past long gone. But light is not immune to the universe's restless growth. As it travels across billions of years, the very fabric of space stretches it, pulling its wavelength longer, robbing it of energy. This phenomenon, known as cosmological redshift, is more than a quirk of physics. It is the universe itself speaking, telling us how far it has expanded since the light began its journey. To understand redshift, picture a wave drawn on the surface of a balloon. As the balloon inflates, the wave stretches along with the rubber. Its peaks spread apart and its wavelength grows. Now imagine light waves traveling through an expanding universe. They, too, are stretched as space grows around them. The result is a cosmic fingerprint. Light emitted as blue or green arrives on Earth shifted toward red, or even beyond into invisible infrared. This stretching is not the same as the Doppler shift we experience when a siren passes by. The Doppler effect happens because a source moves through space relative to you. Cosmological redshift, however, happens because space itself is expanding. Galaxies are not zooming away like rockets. Instead, the space between us and them grows. And the light waves traveling through that space are dragged along for the ride. Astronomers use this effect like a ruler. The greater the redshift, the more space has expanded since the light was released. In fact, the relationship is so precise that measuring a galaxy's redshift allows us to estimate its distance with remarkable accuracy. But redshift reveals something even stranger, something that forces us to confront the limits of what we can ever know. Consider this: the universe is 13.8 billion years old. So you might think the farthest object we could see should be 13.8 billion light years away. But that's not the case. The most distant objects we can observe actually sit 46 billion light years away. How can that be? The answer lies in expansion. When the light from those galaxies began its journey, they were much closer. But during the billions of years that light traveled, space itself kept stretching. By the time the photons reached us, those galaxies had been carried far, far away, so far, in fact, that they now lie 46 billion light years from Earth. This defines the observable universe, a bubble with Earth at its center and a radius of 46 billion light years. Everything inside that bubble is potentially visible to us. Everything beyond it, forever hidden. No telescope, no matter how powerful, can reach across the expanding gulf. This boundary is called the cosmic horizon, and it is not static. Every second, new regions of space become visible as light has more time to travel, but expansion works against us. While the horizon slowly grows, Galaxies near its edge are being dragged away faster than the speed of light. Over time, they will slip out of reach. Think of it like a treadmill moving in the opposite direction. You take steps forward, light traveling toward us, but the treadmill of expansion moves backward even faster. Eventually, the light cannot keep up. Beyond a certain distance, photons can never close the gap. This cosmic horizon means that most of the universe is permanently off limits. There could be galaxies, stars, even civilizations just beyond that invisible line, but we will never detect them. Expansion enforces a kind of cosmic censorship. The consequences are sobering. Today, our observable universe contains about 2 trillion galaxies. Each one holds hundreds of billions of stars, more suns than grains of sand on all the beaches of Earth combined. And yet, this staggering number represents only a fraction of what exists. The majority of the cosmos lies forever out of reach, hidden beyond the horizon, and it gets stranger. The observable universe is shrinking in terms of what we can see. Not in size, remember, it's 46 billion light-years across, but in population. As expansion accelerates, galaxies near the edge of visibility are pushed past the horizon. One by one, they disappear, not with a flash or an explosion, but with a slow fading, their light stretched until it can no longer reach us. In the far future, only the galaxies of our local group, the Milky Way, Andromeda, and a handful of smaller companions will remain visible. The rest will be erased from view by the relentless growth of space. So what does this mean for light itself? Every photon becomes a time capsule of expansion. Consider a photon emitted by a galaxy 10 billion years ago. Back then, the universe was smaller, denser, hotter. As the photon journeyed through expanding space, its wavelength stretched, its energy diminished. By the time it arrives on Earth, it no longer carries the same identity it had when it left. It has been reshaped by the universe itself. Ultraviolet light might arrive as visible red. Visible light might arrive as infrared. Infrared radiation might be stretched into microwaves. In extreme cases, high-energy gamma rays are transformed into faint radio waves. The very nature of light changes as the universe evolves. This cosmic stretching also explains why distant galaxies appear so dim. Imagine lighting a candle and placing it just a few feet away. It blazes brightly. Move it a mile away and it still glows, though fainter. Now imagine carrying that candle across billions of light-years of expanding space. By the time its light reaches you, expansion has drained much of its energy. Galaxies that actually shine brighter than trillions of suns appear as faint smudges, barely detectable in our telescopes. The James Webb Space Telescope, JWST, was designed specifically to capture this ancient, stretched light. Its instruments operate in the infrared, the perfect range for detecting photons that began their journey as visible or ultraviolet light but were stretched into infrared over billions of years. With JWST, astronomers can peer back to the universe's earliest galaxies, formed only a few 100 million years after the Big Bang. But even JWST cannot pierce the ultimate wall, the cosmic microwave background, CMB, that ancient glow marks the earliest light that could ever travel freely. Anything before that, the first 380,000 years of the universe, is hidden from view. To study that epoch, scientists must rely on indirect evidence, such as gravitational waves or theoretical models of inflation. The redshift of the CMB itself is extreme. When it was released, this radiation glowed like the surface of a star, around 3,000 degrees Celsius. Today, expansion has stretched it into faint microwaves, cooling it to just 2.7 degrees above absolute zero. That faint glow fills the sky, a constant reminder of our fiery beginnings. So redshift is more than a measurement. It is a cosmic language, a translation of the universe's expansion into wavelengths of light. It tells us not only where galaxies are, but how far they've traveled in time. It defines the limits of our cosmic vision, sketching a boundary between the known and the unknowable. Every night, when you look at the stars, you are not seeing the universe as it is, you are seeing it as it was. Some of the light reaching you. Tonight began its journey when dinosaurs roamed Earth. Some began long before Earth even existed. And some began so early that it carries whispers from the dawn of time. The cosmos is not just a place, it is a history book written in light. And with every photon stretched, every redshift measured, we turn another page in that ancient story. Dark energy and the fate of the universe. For most of human history, we believe gravity ruled the cosmos. From the apple falling on Newton's head to the planets circling the sun, gravity seemed to be the ultimate architect. Even Einstein's general relativity showed how gravity bends space itself, guiding the dance of stars and galaxies. So, naturally, scientists assumed the expansion of the universe would eventually slow under gravity's pull, but the universe had a surprise waiting. In 1998, two independent teams of astronomers studied distant stellar explosions known as Type Ia supernova. These explosions are cosmic lighthouses, always shining with nearly identical brightness. It makes them perfect distance markers. By comparing their true brightness with how dim they appear, astronomers can calculate how far away they are. Combine that with their redshift, and you get not just distance but the speed at which the universe was expanding when the light was released. The results stunned the world. Instead of slowing down, the universe's expansion was speeding up. Something unknown was pushing galaxies apart, overpowering gravity on the largest scales. Scientists gave this mysterious force a haunting name, dark energy. The name is really a confession of ignorance. We don't know what dark energy is. We can't see it, touch it, or detect it directly. Yet, it makes up nearly 68% of the universe's total energy budget. Ordinary matter, the stuff of stars, planets, and people, accounts for less than 5%. Dark matter, another invisible ingredient, adds about 27%. That means 95% of reality is made of things we do not understand. So, what exactly is dark energy? The leading theory suggests it might be the energy of empty space itself, born from quantum fluctuations. According to quantum physics, even a perfect vacuum isn't truly empty. Instead, it seethes with virtual particles that appear and vanish in a constant froth of activity. This vacuum energy could create a constant push, driving the acceleration of expansion, but there's a problem. Quantum physics predicts a vacuum energy so immense it would blow the universe apart instantly, a value larger than observations by 120 orders of magnitude. To put that in perspective, it's the single worst prediction in the history of physics. Other ideas propose that dark energy might emerge from hidden dimensions beyond the three we perceive. Some theories suggest it isn't constant at all, but evolves over time, growing stronger or weaker as the universe ages. Recent observations even hint that dark energy could be changing, a clue that would rewrite the foundations of cosmology. Regardless of its true nature, dark energy dominates the future. If it remains constant, galaxies will continue drifting apart forever. Stars will burn out, galaxies will fade, and the universe will approach a state called heat death, cold, dark, and lifeless, stretched so thin that nothing interesting ever happens again. But if dark energy grows stronger, the future could be far more dramatic. Imagine a scenario called the Big Rip. Over trillions of years, acceleration increases so violently that it tears apart galaxy clusters. Later, it pulls individual galaxies apart. Eventually, stars are ripped from their orbits, planets are torn from stars, and finally, even atoms themselves are shredded as space stretches faster than the forces holding matter together. The cosmos itself dissolves into nothingness. On the other hand, if dark energy weakens, gravity might eventually regain control. Expansion could slow, stop, and even reverse. In that case, the universe would collapse back into a fiery singularity. In a big crunch, a mirror image of the Big Bang. Our current evidence favors a middle path, a universe that expands forever, with acceleration continuing at a steady pace. In that case, distant galaxies will keep crossing the cosmic horizon, vanishing from view until only our local group remains. The night sky, billions of years from now, will be almost empty, an ocean of darkness with only a handful of faint island galaxies surviving. And yet, the numbers hide an even deeper mystery. The density of the universe seems to sit precisely at a critical value, the razor's edge between collapse and runaway expansion. It's as if cosmic forces are perfectly balanced. Too much matter, and gravity would have pulled everything back long ago. Too little, and the universe would have torn itself apart before galaxies could form. Instead, the density hovers at exactly the value needed to allow billions of years of cosmic evolution. Why? Some scientists argue it's just luck, a cosmic coincidence. Others invoke the multiverse hypothesis that countless universes exist with different properties, and we happen to live in one where the numbers permit life. Still, others suspect there is some undiscovered principle of physics that forces the universe toward this delicate balance. Dark energy complicates the puzzle even more. Unlike matter, which thins out as space expands, dark energy's density appears to remain constant. That means the total amount of dark energy increases as space grows. It's as though the universe creates energy out of nothing. Every second, more dark energy appears, fueling more expansion. In a runaway feedback loop, even stranger, dark energy doesn't clump like matter. It doesn't form clouds or galaxies. It appears perfectly uniform, filling every corner of space with identical density. It is smooth, invisible, and relentless. So here we are, small beings on a tiny planet, realizing that everything we see, every galaxy, star, and atom accounts for just a sliver of what exists. The overwhelming majority of the cosmos is controlled by an invisible force we cannot touch or measure directly, and yet, by studying faint supernova and stretched starlight, we've glimpsed its presence. We've learned that it will shape not only the destiny of galaxies, but the fate of existence itself. The story of dark energy is both humbling and terrifying. It reminds us that we live in a cosmos still full of secrets. It reminds us that the future of everything from stars and galaxies to atoms and life itself rests in the hands of a force we do not understand, and as if that weren't enough, the mystery deepens further. Because when astronomers measure how fast the universe expands today, they don't all get the same answer. A growing tension in the data suggests our understanding of expansion itself may be incomplete. And here, the James Webb Space Telescope steps into the spotlight. The cosmic crisis and beyond. For decades, astronomers believed they were closing in on a precise description of the universe. The Big Bang explained its beginning. Inflation smoothed its early chaos. Redshift and the cosmic microwave background mapped its growth. Dark energy explained its accelerating future. It seemed like the puzzle pieces were falling into place. But then came the crack in the picture. The Hubble tension. The Hubble constant is the number that tells us how fast the universe expands today. Two independent methods should yield the same value. But they don't. The first method looks to the deep past. By studying the cosmic microwave background, CMB, the afterglow of the Big Bang, scientists can model how the universe expanded over billions of years. This approach, most famously measured by the Planck satellite, predicts a current expansion rate of about 67 kilometers per second per MegaParsec. The second method looks at the nearby universe. By measuring distances to galaxies using standard candles like Cepheid variable stars and Type Ia supernova, astronomers can directly observe how quickly galaxies are receding today. These local measurements give a higher value, around 73 kilometers per second per MegaParsec. The gap is only about 9%. But the precision of both methods is so high that the discrepancy cannot be brushed aside as error. Something fundamental is wrong. Enter the James Webb Space Telescope, JWST. With its infrared eyes, Webb can pierce dust clouds and measure Cepheid variables with unprecedented accuracy. Many hoped it would resolve the Hubble tension by showing that local measurements were flawed. Instead, Webb confirmed them. To within 1%, its results matched the higher expansion rate. This left cosmologists stunned. Two independent methods, both refined to extreme precision, continue to disagree. The Hubble tension isn't a mistake, it's a mystery. And that means our standard model of cosmology, successful as it has been, is incomplete. So what could be happening? Some scientists suggest early dark energy, a temporary force that sped up expansion in the universe's youth before fading away. Others propose hidden interactions between dark matter and dark energy, subtle forces that change expansion in ways we haven't imagined. There are even ideas involving extra dimensions, where gravity leaks into hidden realms, altering cosmic evolution. And then there are the radical possibilities. One proposal is that our universe is not alone, but part of a vast multiverse. In this view, countless universes bubble into existence, each with its own laws of physics. Some expand too fast, tearing themselves apart before galaxies can form. Others expand too slowly, collapsing almost immediately. We happen to live in one of the rare universes balanced just right for stars, planets, and life. But the multiverse isn't just an abstract thought. Some theories of inflation suggest it naturally produces endless pocket universes. Our universe is just one patch in a cosmic foam, and its expansion might even be influenced by collisions or interactions with neighboring realities. Some physicists have speculated that what we call dark energy could actually be the gravitational tug of invisible universes brushing against ours. Of course, these ideas remain speculative and critics argue that they're untestable. But the Hubble tension has forced cosmology into uncomfortable territory. Either the early universe was different from what we think, or the fundamental physics governing reality needs revision. And while we debate the causes, expansion marches on. Today, we live in a universe rich with galaxies an estimated 2 trillion within our observable horizon. But fast forward tens of billions of years and the night sky will look very different. Galaxies now at the edge of visibility will vanish beyond the horizon, then more will follow. Eventually only our local group, the Milky Way, Andromeda, and a few dwarfs will remain bound together by gravity. Everything else will fade into darkness. Farther into the future, stars will exhaust their fuel. The universe will grow cold as stellar birth ceases. Black holes will dominate, swallowing what remains, only to evaporate over unimaginable timescales through Hawking radiation. In the end, all that will remain is a thin soup of particles scattered across an ever-expanding void. This is the likely fate dictated by dark energy, a slow, quiet ending called heat death, yet some possibilities are more violent. If dark energy grows stronger over time, the big rip awaits, tearing galaxies, stars, and even atoms apart. If it weakens, a big crunch could reverse expansion, collapsing everything back into a final singularity. Each scenario underscores a truth, both humbling and profound. The universe's future depends on a force we barely understand, but perhaps the greatest lesson of the Hubble tension is this: science is not a finished book. It is a story still being written. The universe keeps surprising us. Every time we think we've figured it out, it reveals another twist. Think about what that means. We live in a cosmos where 95% of existence, dark energy and dark matter remains, invisible and mysterious, where light from most of reality will never reach us, where even the number describing how fast space expands refuses to agree with itself, and yet, with fragile instruments orbiting a small planet in a quiet corner of one galaxy, we can measure these things. We can detect the fading afterglow of the Big Bang. We can watch galaxies flee into darkness. We can sense invisible forces that shape the destiny of everything. Perhaps one day, new physics will explain dark energy. Perhaps we'll discover that our universe is just one bubble in an infinite multiverse. Or perhaps we'll learn that reality itself is stranger than any theory we can imagine. Until then, the expansion continues. Every second, more space is created. Every second, galaxies slip farther away. Every second, the horizon between the known and the unknowable grows. The universe is not a static picture. It is a living, evolving story, a story we are only beginning to read. And whether its final chapter ends in heat death, a big rip, a big crunch, or something beyond our imagination, one thing is certain: the greatest mystery of all is that we are here, at this brief moment in cosmic history, able to witness it.